Okay, hello. Here we have a problem. This is number 2 from the homework. The assignment was final assignment on matrices, and the situation, or the problem was, here is a seemingly routine system of 3 equations and 3 variables, but instead of being given kind of all the information about the system, there is a sort of unknown letter A, and this A, because you don't know what it is, it's going to sort of play a role in the answer, or rather, the sort of solution to the system of equations is going to be in terms of A, I guess you would say. And the actual directions are under what conditions, in other words, for what values of A is it the case that this system has no solutions, one solution, or an infinite number of solutions? Okay, so I think the best way to do this problem is to just be extremely confident about your abilities in solving systems of equations and just mostly do the same normal thing that you would do. And then at the end there's some sort of thinking to do. Okay, so I actually don't remember exactly how to do this, but I think we'll just start and it will be okay. So step 1, I'm going to convert this to a matrix because that seems like the easiest thing to do. So this is 1, 1, negative 1, 1, and here we have 2, 3, A, 3, and 1, A, 3, 2. Okay, great. So I'm just going to do Gaussian elimination like normal and sort of see what happens. Alright, well, let me just double check my numbers really quick, make sure I'm not doing anything wrong. X, A, 3, 2. Yeah, okay. Whew. So, we begin doing the same old thing that you always do. You start with a 1 up in the top left corner, which is conveniently already there, and you use it to strategically get rid of the stuff beneath it. So I will replace row 2 with negative 2 row 1 plus row 2, and I will replace row 3 with negative row 1 plus row 3. Okay? Well, I get 1, 1, negative 1, 1. Then, let's see what else happens. Okay, so I get 0, 1, A plus 2, okay, so that's just A plus 2, and 1, if I did that right. Let me just double check again. Yeah, A plus 2 and negative 2. Whew. Oh, man. Okay, now I do boom boom, so that becomes a 0, and then here I get negative 1 plus A, so that's A minus 1. And here I get 4, I guess. Oh. And then 1. Is that right? Yeah. Oh man. 1, 3 is 4, and negative 1, 2 is 1. Okay. So here I am, kind of like this now. Okay. Oh man. Now what? Well, so far I think I'm okay. I just have to be comfortable with the fact that some of these coefficients are in terms of A, but okay, let's not be scared by that. What would we do next? The next thing we would do is, the next thing we would do is we would make this a 1, well it already is, and we would use that 1 to clear some space underneath. Okay, so let's do that now. I'm going to sort of insert a step, which is a little bit optional, but I think is helpful. Let's multiply through this line by A minus 1. After all, A is just a number. It's a constant. So, all right, what I'm going to do is I'm going to replace row 2 with A minus 1 row 2. I think this is helpful. So that gives me 1, 1, negative 1, 1. And here I get 0. Well, now I'm multiplying A, so that becomes an A minus 1. But now here, okay, now I need to maybe be a little bit careful. Now I get A minus 1, A plus 2. 1. No, sorry, this will also be a minus 1. And here I didn't do anything. Okay, so this is looking complicated, but if you just sort of stay focused, didn't really do anything yet. I just put the system directly into the matrix, did Gaussian elimination carefully, hopefully not making any mistakes. And here I sort of inserted this preliminary step to multiply row 2 by a minus 1, just so I could kind of subtract now. That's the point, right? Let's do it. Let's now. Well, I'm going to do a couple things. Well, the main thing I'm going to do is I'm going to subtract. That was the whole reason to multiply row 2 by a minus 1, just so that those numbers would be the same, just to make it a little bit easier on my brain. So now I subtract. So alright, so this is going to give me, well, I'm going to do the final line. So in fact, I'll just do R2 minus R3. Okay, well, I get 0, 0, and now sort of what goes here? What goes here is a minus 1, a plus 2 minus 4. Alright, so let's just off to the side, let's just do that. What is a minus 1, a plus 2 minus 4? I'm just kind of doing some scratch work so to keep my kind of matrix clean. Alright, well, I think the only thing to do is to multiply this out and see if it simplifies. So that gives me a squared plus 2a minus a, so that's plus a, and then minus 2 minus 4. So altogether minus 6. And actually that can be factored as a plus 3, a minus 2. So this right here is a plus 3, a minus 2. Might need a little bit more space here. Because then this will be a minus 1 minus 1, so that's a minus 2. Chop, chop, chop. Okay, and I didn't do anything to this first row, but for the second row I might as well sort of put it back again, right? I mean, I had it kind of nice and simple, and then I multiplied by a minus 1, but that sort of did its job, so I'm going to divide back through again. Okay, so that takes me back to 0, 1, a plus 2, 1. Okay, so, great. Once again, so far, assuming I'm already an expert on Gaussian elimination and understand everything that I'm doing, then I have not done anything complicated yet. I've just pursued kind of nice, neat, clear, careful work. And now I find myself basically done. And when I say basically done, I mean I have this kind of triangle of zeros here, so I could do sort of more, but Gaussian elimination sort of stops, or can stop at least, once you get this triangle of zeros. Okay, and now it's time to start sort of thinking about what we have here. And I guess the answer goes like this. What's sort of one observation? Well, one immediate observation is, if a is 2, okay, so if a is 2, then I think I'm ready to say something. And the thing I'm ready to say is that in the case where a is 2, this is a 0 and this is a 0. In other words, if a is 2, then the system of equations we have is in fact x plus y minus z equals 1. Here we have y, if a would be 2, then that would be 4, so plus 4z equals 1. But then this final row is just 0 equals 0. And so in the case in which a is 2, we in fact just have a system of equations in which one of the lines is one of the equations is not really there at all. And alright, so we know from our experience with solving these systems that means that this system is going to have an infinite number of solutions. And in fact, if we think of these two equations as representing planes, those two planes will intersect, and so we'll get a line here. And since we pursued equivalence preserving operations all the way through, that tells me that if a was 2, that my original system of equations also had an infinite number of solutions. So already I'm going to say right now that if A equals 2, we have an infinite number of solutions. Okay, great. Well, now that I've sort of taken care of that case, now I can maybe pursue the if A is not 2 case. And well, if A is not 2, then I'm free to divide both sides of this third equation by A minus 2. And so if A is not 2, then I'm just going to do that, because that's a sort of simplifying step that I can do, which is to divide row 3 by A minus 2. Okay, so that gives me 1, 1, negative 1, 1. Here I get 0, 1, A plus 2, 1. And here I get 0, 0, A plus 3, 1. Okay, so, good. Okay, well, now, what can I say about this situation? Well, I think it's important to sort of remember what this system of equations represents. So perhaps for clarity, maybe it's worth it to once again put this back into sort of more expanded form with the variables still there. X plus y minus z equals 1. This is y. Now here, I don't know what a is yet, so this coefficient is going to be, a plus 2 z equals 1. And finally, we get a plus 3 z equals 1. Okay, well now, I think clearly from this case, but also if you're comfortable looking at this matrix and seeing sort of in your mind this system of equations, then this last step wasn't even necessary. But I think I'm ready to say right now another observation. And another observation, because we have seen that whenever a system of equations has no solutions, you can sort of keep doing the Gaussian elimination until okay, whenever a system of equations has no solutions, what you end up with is kind of a contradictory sentence. And alright, I guess there's multiple ways of thinking about this, but if A is negative 3, then we have problems. Because if A is negative 3, then the final row of this matrix here is in fact just 0, 0, 0, 1. And maybe alternatively we could look at this representation here and see that if A is negative 3, then the final equation here is, maybe I'll even just write it, if A is negative 3, then what we just have is x plus y minus z equals 1. Y, if A is negative 3, then that's just minus z equals 1. But the important part is that this is just 0 now, that this is 0 equals 1. And so I think I'm ready to state my second conclusion. My second conclusion is that if A is negative 3, then we have no solutions. Okay, so just want to get keeping this organized. On the one hand, if A is 2, we have an infinite number of solutions. If A is not 2, then I subsequently notice that if A is negative 3, then there are no solutions. So now maybe the last thing to do is to say, okay, well, it's sort of an if-else type thing, right? If A is not 2, then perhaps it's negative 3. But if not, so if A is not 2 and A is not negative 3, then what? Well, now, if A is not negative 3, then perhaps the sort of final thing to do is just to divide by A plus 3. And so if I produce that matrix, the matrix in which row 3 was divided by A plus 3, and I know I'm allowed to divide by A plus 3 because I know A is not negative 3, then sort of my final answer is 1, 1, negative 1, 1, 0, 1, a plus 2, 1, and 0, 0, 1, 1 over a plus 3. And if you are, okay, cramming this into this tiny little space, if you are comfortable with this matrix, then you don't even need to do what I'm about to do now. But if you're, if it helps you, realize that this is saying x plus y minus z equals 1, y plus a plus 2z. I still don't know what a is, but I think it doesn't matter right now. And down here, this is saying that z is 1 over a plus 3. So in fact, if a is not negative 2 and a is not negative 3, then what's going on in our system? Well, then whatever a is, say if a is 5 or something, then z is just 1/8, and then in fact this system is totally fine. So the sort of final thing is that if, maybe I'll just write it right here, if a is not 2 and a is not negative 3, then we're going to have one solution. And the fact that we have exactly one solution maybe can be sort of shown by this final matrix or that final system of equations, which is the exact same thing, which just shows that, well, whatever a is, if it's not 2 and not negative 3, you simply stick it in right there and you have an explicit solution for z. Z is just 1 over a plus 3 is in fact the solution. And now that you know what z is, you can use that value for a and this value for z, plug it back in, solve for y, solve for x, and in fact that's what you have. Okay, so the sort of value, I guess, in doing this problem is in sort of being, I guess, comfortable enough with the sort of three possible things that can happen when you solve a system of 3 equations in 3 variables. One thing that can happen is that you get a row of all zeros, and we know that when you get a row of all zeros, that we really only have 2 equations, and so there'll be an infinite number of solutions, and that row of all zeros occurs when a is 2. But on the other hand, another thing that can happen is you get 0, 0, 0, some number kind of situation. And that is equivalent to having a sort of just a false statement. This is the other kind of end game for solving a system of 3 equations in 3 variables, and then there will be no solution. And then the third thing that can happen is that the system of equation does have a solution, and if it does have a solution, then you just happily do Gaussian elimination all the way until you get, 0, 0, 1, something, and that's really just another way of saying z is that thing. So that fully answers the question, and hopefully that was helpful.